Welcome to Colonize the Ocean podcast, where we discuss oceanic colonization, exploration, and education with your hosts Adam Jewell and Brendan Traxler.
Imagine dedicating 5 hours of your day, 5 whole hours, to prepping, traveling, dealing with all the necessary, bureaucracy, just to get one single hour of actual meaningful work done.
It sounds like a completely absurd way to run an operation, doesn't it?
It does, but for marine biologists who rely on traditional diving techniques, well, that isn't just a bad day at the office.
No, that's their deeply frustrating daily reality. It's an exercise in extreme, almost prohibitive inefficiency.
And that inefficiency, it must just profoundly limit the scope of what we can even attempt to study in the ocean.
Oh, absolutely. The effort spent just getting to the dive site, managing all the constraints of pressure, and, sticking to these incredibly strict decompression protocols.
Right.
It means that the research we gather is almost always a brief, often very expensive snapshot of a vast and complex environment. We are constantly playing beat the clock.
Exactly. But what if we could eliminate that travel time? What if we could just get rid of those minute-by-minute decompression penalties and allow humans to live beneath the waves for not just an hour, but for weeks or even months at a time?
Well, that concept, that capability is no longer just confined to the pages of a Jules Verne novel.
And that's what we're talking about today.
Today, we are taking a deep dive into Vanguard. This is the new subsea human habitat, designed and built by a really pioneering organization called DEEP.
And based on the insights we've drawn from a recent New Scientist report detailing its unveiling, Vanguard isn't just some new scientific tool.
No, it is poised to completely revolutionize our fundamental access to and our understanding of the majority of our planet.
So our mission for you, the learner, is to quickly grasp the significance of this profound technological and, philosophical shift. We're moving from this constrained, short burst kind of marine research to a whole new era of deep immersive exploration. We really want you to understand the physics that holds us back and the technology that is now pushing us forward.
I think the scale of this change is best captured by Dawn Kernagis. She's DEEP's director of scientific research.
Okay.
And she argues that having people return from this subsea experience is going to, and I'm quoting here, open our eyes to the underwater world like astronauts did with space.
Wow, that's a powerful analogy.
It really is, and it's vital because it suggests a total paradigm shift in how we view the final frontier right here on Earth. Astronauts didn't just, visit orbit. They established a continuous human presence.
And that is what DEEP is aiming for beneath the surface.
That's the goal.
Okay, let's unpack this shift, because when you look at the raw numbers, the current system is so fundamentally broken that Vanguard becomes an obvious necessity. We need to start by detailing just how constrained marine research is right now.
It's an issue of logistics crippling science. As Roger Garcia, he's DEEP's director of habitat operations, points out, the current workflow for marine researchers is optimized around a boat schedule and the constraints of the gas laws, not around scientific productivity.
Right. The science has to fit the schedule, not the other way around.
Precisely.
So let's break down that 5-hour investment we mentioned. First, you've got the travel time, right? Getting from the lab or your car down to the shore, loading all the specialized equipment.
Which is heavy and cumbersome.
And then the boat journey out to the remote research site. That's already hours gone, and you're often fighting weather or currents the whole way.
Then you have the whole pre-dive process, the rigorous gear checks, the safety protocols, the descent itself. But the true scientific killer, it's the mandatory decompression stops.
Okay, explain this for us. When a diver breathes compressed air or, nitrox at depth, what's happening in their body?
So, inert gases, which is primarily nitrogen in the air we breathe, they dissolve into your body tissues under the ambient pressure. Your body just soaks it up like a sponge.
And as they come back up to the surface, those gases need to come out of those tissues slowly.
Very slowly. If you ascend too quickly, Those dissolved gases, that excess nitrogen, it comes out of solution way too rapidly. It forms bubbles in your blood and your tissues.
Which is decompression sickness or the bends.
Exactly. And it can be crippling or even fatal. That's why those stops on the way up are absolutely non-negotiable for safety.
And for a typical dive to a research depth of, maybe 150 feet or so, those decompression stops can add a significant amount of time to the whole ascent profile.
A huge amount of time.
Yeah.
And the source material confirms it. This entire process, the travel, the prep, the mandatory stops, it eats up 4 or 5 hours of a highly specialized researcher's day.
And what do they net from all that?
About an hour's worth of actual underwater work.
One single hour of data gathering or maintenance for 5 hours of logistical investment. It's a brutally low return.
And like you said, it forces researchers to conduct science through these tiny snapshots. It limits them to really simple tasks or heavily monitored short-duration experiments.
You can't really study a process that takes hours to unfold.
No, it's the very definition of a constrained system. You can't initiate a complex, long-duration experiment or truly track dynamic, time-sensitive ecosystem interactions when your presence is limited to 60 minutes a day, often separated by a full 24 hours.
It just severely limits our ability to move from just cataloging the ocean to actually understanding its deep, continuous processes.
Yeah.
So if the constraints are all defined by these physical gas laws, how does Vanguard fundamentally change the physics? The key, as you mentioned, is this concept of saturation diving.
Saturation diving completely flips the script on that whole decompression penalty.
How so?
Instead of treating every dive as a temporary invasion of the pressure environment, you accept the pressure as your home. You live there. You eliminate the constant need for these long, slow decompression stops after every single trip outside.
So explain the process of saturation for us. What is happening physiologically? What's going on inside the Aquanauts' bodies?
Okay, so when a diver lives under pressure for an extended period, it takes about 24 to 48 hours, depending on the inert gas they're breathing. Their body tissues absorb that gas until they can't hold anymore.
They reach maximum capacity.
Exactly. Equilibrium with the ambient pressure, that state is saturation. But, and this is crucial, at the depths Vanguard is designed for, you cannot use regular air or even nitrox, which is just oxygen-enriched air.
Right. Why not? What's the problem with nitrogen at those depths?
Well, when you go deeper than about 100 feet while breathing air, the high partial pressure of nitrogen starts causing something called nitrogen narcosis.
The rapture of the deep.
That's the one. It's a state very similar to intoxication that severely impairs your judgment, your cognitive function. It's incredibly dangerous. Furthermore, the oxygen in the air actually becomes toxic at higher pressures.
Toxic.
It can lead to central nervous system or CNS toxicity, which can cause convulsions and ultimately death. So, air is just not an option for this kind of work.
So the solution is you have to swap out the problematic gas. You have to change what you're breathing.
Precisely. For deep saturation, divers must switch to a gas mixture where nitrogen is replaced by helium. This is typically a mix called heliox, just helium and oxygen.
And what makes helium so much better?
Helium is far less soluble in lipids, in fatty tissues, which means it causes negligible narcosis. It allows for clear thinking at great depths. However, it still dissolves and saturates the other tissues in the body.
So once the Aquanauts are fully saturated with this helium and oxygen mixture at the habitat's depth, what does that do to the clock?
This is the magic of saturation. Once your tissues are fully saturated, staying at that depth for 1 hour or 1 week or 1 month. It makes absolutely no difference to the total decompression time you'll need to return safely to the surface.
Really?
Really. That final long decompression is based solely on the depth of the habitat and the gas mixture you were breathing, not the duration of your stay.
That is the core breakthrough right there. You functionally eliminated the daily clock.
You have.
You could stay out for hours, go back to the habitat, rest, have a meal, and go back out again without resetting a long, complex decompression schedule every single time.
And Vanguard capitalizes on this efficiency exponentially. Roger Garcia confirms the practical results. Once you're saturated, the logistics change from that 5-hour preparation and recovery ordeal to a mere 15 minutes.
15 minutes.
15 minutes. That includes putting on your gear, going through basic checks in the habitat's wet porch, and locking out into the ocean.
Just think about that conversion. A 15-minute prep time translates into up to 9 hours of effective research time per person, per day.
It's not just an improvement, it's a fundamental transformation in scientific capability. You turn an expensive, constrained day trip into an extended, productive work shift.
It allows the science, the research itself, to dictate the schedule, not the physics of diving.
Exactly. You move from what was a logistics challenge to a scientific marathon. You're giving researchers the time they actually need for complex tasks, large-scale sampling, and I think this is the most important part, continuous observation.
And that huge efficiency boost leads us directly to discussing the physical manifestation of this new paradigm. Vanguard itself. What do we know about the specs of this pilot habitat?
Well, Vanguard is the platform for all this change. It was designed and built by Deep, and it was just unveiled in Miami in October.
And it's specifically designated as a pilot habitat, right? So it's proof of concept.
That's right. It's relatively modest in size, and it's designed to prove the concept works, to refine all the life support systems, and to test the procedures for future, larger expansion.
Modest, but still capable of facilitating a sustained human presence underwater.
Oh, absolutely. It's designed to house up to 4 Aquanauts, and the intention is for missions lasting weeks or even months at depth.
Which is only possible because they've built in true habitation facilities. I mean, this isn't just a pressurized metal cam.
No, not at all. It includes designated living and sleeping spaces, basic sanitary facilities, and crucially, a workspace, a lab.
Yeah, and that dual-function habitation and laboratory, that's what makes this so state-of-the-art. It's not just a decompression chamber you visit. It's a fully equipped, pressure-equalized research lab that you live in.
Exactly. And this brings us to the second massive scientific leap that Vanguard facilitates: the ability to maintain sample integrity by processing those samples at depth.
Ah, yes. This is where the physiological research gets revolutionary.
It really does.
This is a point that Don Kernges really focused on, and I think it's often missed in discussions about deep-sea exploration. We think about the integrity of, say, a water sample, but what about the integrity of a human blood sample taken from one of the divers?
That's the problem. When you bring any delicate sample, whether it's biological or environmental, up to the surface, it experiences this radical, rapid drop in hydrostatic pressure.
And that's usually compounded by changes in temperature and light.
Right. And this physical stress immediately alters the sample's molecular state.
It's like throwing a delicate laboratory experiment across the room right before you measure the results. The shock of the throw becomes the dominant signal you measure.
That's a perfect analogy. Kernagis noted that for physiological studies on the divers themselves, the act of decompressing introduces these massive stress factors that can completely mask the long-term, subtle data researchers are actually looking for about high-pressure adaptation.
Okay, so give us a concrete example of that masking effect. How does the decompression process actually contaminate the data?
So she specifically highlighted RNA expression levels in the diver's blood.
Right, which tells you which genes are active.
Exactly. RNA expression is essentially the cellular blueprint for creating proteins. It shows us exactly which genes are turned on or off and what the body is trying to build or repair in real time. Decompression, being a massive physiological stressor, triggers this huge inflammatory cascade.
And that acute inflammatory response, the body basically freaking out about the pressure change, it shows up as a distinct, measurable signature in that RNA expression profile.
Yes. It's like sudden, loud static drowning out a quiet, important signal. The researchers were seeing the signal of decompression stress, which included the rapid upregulation of specific inflammatory cytokines and heat shock proteins.
And that signal was so strong it was contaminating or drowning out any of the other subtle changes they were trying to find.
Well, one's related to the long-term effects of just living at constant high pressure.
Yeah. So if they wanted to know how, say, 3 months of hyperbaric living changes a person's baseline metabolic rate, they couldn't get a clear reading because the sample processing itself, the act of bringing it to the surface, introduced this huge, new, irrelevant variable.
That's it, exactly. Physiologists absolutely require samples that are taken in situ under pressure to achieve an uncorrupted baseline understanding of human adaptation.
So Vanguard needs to be equipped with a full lab.
A specialized hyperbaric laboratory. Things like centrifuges that are capable of spinning blood samples under pressure, and specialized microscopes. Things that can stabilize and analyze these delicate biological samples before they ever experience the pressure change of ascent.
It's a huge fundamental leap forward in hyperbaric medicine.
No question.
It makes the Vanguard habitat not just a base camp for marine science, but a dedicated subsea Human Physiological Research Center. It's tackling two frontiers at the exact same time.
It truly is. And having discussed the human element, let's pivot now to the more traditional marine science applications that are now just dramatically amplified. Let's start with the area that is perhaps most critical right now, coral restoration.
This is where that massive time amplification immediately pays off, I would imagine. Both Jim Britson, who is the founder of Sustainable Oceans and Reefs, or SOR, and Don Kernagis, expressed just extreme enthusiasm for the implications here.
And the reason is simple. Coral growth is biological, and it is slow. The human intervention required to restore reefs, what they call gardening, is meticulous, repetitive, and very, very time-consuming.
Right. You can't rush the biology, but you must maximize the human labor hours available to nurture it.
Precisely.
So describe some of the work involved in coral restoration. I mean, it's more than just putting down a big block of concrete with some coral on it, right?
Oh, far more. It involves highly specialized techniques like microfragmentation, where small pieces of coral are cut and then encouraged to fuse together and grow much faster than they would normally.
Okay.
Then you have the complex process of actually attaching them, using specialized underwater epoxy or cement or ties to these nursery structures or directly onto damaged reefs. Each one of those fragments requires detailed, careful handling.
And if a researcher only has that 1 hour of bottom time per 5-hour day, they might be able to process, what, maybe 50 fragments?
If they're lucky.
Right.
And very efficient.
But with Vanguard's 9 hours of effective work, that number just compounds dramatically. A small team could potentially process thousands of fragments over a few weeks.
It transforms the scale from a small, localized project into a potentially large-scale reef engineering effort. Britson and Kernagis highlight that Vanguard addresses a big gap in restoration.
What's that gap?
The ability to do continuous monitoring and critical maintenance on the coral garden.
Because these coral gardens are incredibly delicate. They need daily, almost constant attention to thrive.
Absolutely. Think about something like algae overgrowth. It's a constantly moving threat that can suffocate new coral fragments. A single daily visit from the surface might miss a crucial window of opportunity to clear a patch.
But Aquanauts living right next door.
They can conduct hour-by-hour maintenance. They can manually clean off competing organisms, check structural integrity, monitor for disease outbreaks. This continuous presence dramatically increases the survival rate of the transplanted corals.
And there's the depth advantage, too. Regular scuba really limits your access to deeper, often more resilient coral communities, the mesophotic ones.
That's right. Vanguard allows this critical work to be done deeper, accessing what are sometimes called the refugia, these deeper, cooler reefs that may be more protected from the increasing sea surface temperatures that are just devastating shallower ecosystems.
So it solves the difficulty of doing large-scale studies and intervention on these deep-water coral communities, which were just too inaccessible for any sustained work before.
It does.
So Vanguard allows researchers to be both gardeners and constant sentinels for these reefs. But beyond that kind of manipulative science, the immersion capability fundamentally changes observational science. It allows researchers to truly observe the ocean's inner rhythms.
Yes, this is the qualitative shift. It's moving from observing the ocean from the outside to immersing ourselves within it. You transition from just analyzing telemetry data to directly witnessing natural processes as they unfold.
And the most spectacular example of this, it's described as the largest daily migration of biomass on Earth, is the diel vertical migration, or DVM.
The DVM is truly one of the planet's great biological pulses. And yet, because it happens in the twilight zone and under the cover of darkness, it remains incredibly difficult to study in any detail.
So what's actually happening?
Every single sunset, vast numbers of organisms. We're talking billions of tons of biomass, including mesopelagic fish, squid, krill. They ascend from the deep, dark depths, sometimes miles deep, to feed on plankton in the shallower, food-rich surface waters.
And then, before sunrise, they all descend again rapidly, plunging back into the dark depths to avoid the predators that hunt by day near the surface.
It's like an oceanic breath, inhaling and exhaling organic matter across the entire water column every single day.
And to be able to observe this immense process from a stationary habitat, with aquanauts maybe making short, frequent excursions into the water column during the ascent and descent, that offers an unprecedented level of insight.
They can observe the behavioral triggers, the complex dynamics between predators and prey, and quantify the sheer magnitude of the energy exchanged in real time from inside the event itself.
It sounds like having a permanent stake in the twilight zone, allowing them to track this massive biological clock and connect it to global processes like carbon sequestration.
Precisely. The DVM plays a crucial role in cycling nutrients and sequestering atmospheric carbon deep into the ocean, and Vanguard allows us to monitor the variables of that process with just unmatched proximity and continuity.
And then there are the transient events, these momentary occurrences that are just impossible to catch during short, sporadic dives, no matter how many you do.
These fleeting moments are so critical. We mentioned mass coral spawning, and that often happens only once a year, and it's driven by these specific, often unpredictable lunar or temperature cues. A surface dive team could miss the entire event.
Or just catch the last few minutes of it.
Right, simply because they couldn't stay down continuously.
But aquanauts living down there for weeks or months have the highest possible probability of catching the entire event, the subtle buildup, the main spawning window, and the aftermath.
It creates the luxury of scientific patience. Other transient events might include the colonization of a whale fall, when a carcass sinks and supports an entire deep-sea ecosystem, or the fleeting interactions of critical predator-prey pairs that define the health of an ecosystem.
Vanguard turns the aquanaut into a permanent resident, just waiting for the perfect scientific moment rather than just hoping to stumble upon it by chance.
That's it.
That deep dive into the environment is fascinating, but now we have to turn the lens back onto the researchers themselves. The breakthroughs in ocean science are huge, but the data gathered on the human factor, Aquanaut Know Thyself, is equally revolutionary.
Yes, this moves us firmly into the realm of human physiology and psychology in extreme environments. Long-term habitation in these high-pressure or hyperbaric environments is guaranteed to change body tissues.
And we just don't have enough sustained, uncorrupted data to understand the long-term consequences.
We don't. We're moving beyond just understanding how to avoid decompression sickness, and we're starting to ask these fundamental questions about human adaptation. Colonize's challenge here is profound. Are these high-pressure adaptations even reversible?
So, if a human lives in equilibrium with that pressure for 6 months, what happens when they spend 3 weeks decompressing back to surface pressure? Do they just go back to normal?
Or have some changes become permanent? That requires longitudinal studies tracking specific biomarkers over months and months. For example, researchers are intensely focused on monitoring the risk of avascular necrosis, or AVN.
And what's that?
It's a severe condition where a lack of blood flow actually kills bone tissue. It's often observed in professional deep-sea divers after years of exposure. Vanguard allows researchers to meticulously track bone density and blood supply metrics in real time under pressure to understand the actual mechanism of how AVN develops.
And a key emerging study area, as mentioned in the sources, is the epigenetic effects of high pressure. Now, that sounds incredibly complex. How does extreme pressure interact with our genetic controls?
Well, epigenetics studies changes in gene expression, so how genes are turned on or off without actually altering the underlying DNA code itself.
And environmental factors are the main triggers for that.
Yes, the hypothesis is that the constant sustained hydrostatic pressure acts as a profound environmental signal, subtly altering things like methylation patterns around specific genes.
So, the high pressure might not physically damage the body, but it could subtly reprogram how the body functions over time, potentially impacting what? Metabolic rates, immune surveillance, maybe even neurological function.
Exactly. Researchers will be tracking whether this environment affects, for example, mitochondrial function, the powerhouses of our cells, or whether it influences the expression of genes related to inflammation or cellular repair.
And because these effects are subtle and they're cumulative, they need that continuous, uncorrupted sampling that only a hyperbaric lab like Vanguard can guarantee.
Right. It allows us to move beyond just treating symptoms to understanding the genetic control mechanisms of human adaptation to high pressure.
This research on human adaptation leads directly to the connection that gets a lot of people really excited. Subsea research as a direct analog for space exploration. Why does NASA care about people living at the bottom of the ocean?
The comparison is often drawn because the ocean environment, especially when you're confined to a closed habitat, shares these critical operational similarities with living in space.
Like what?
You have intense isolation, extreme resource constraints, every liter of air and water must be meticulously managed and recycled, and an absolute reliance on complex technology for your basic survival. For NASA, this is an ideal analog environment for simulating future lunar or Mars missions.
And this isn't a new idea either. NASA has historically used previous undersea habitats like the Sea Lab and Tektite programs back in the 60s and 70s.
And more recently, the NEMO missions.
Yes.
And Colonize, with her direct background as a saturation diver supporting those NASA analog missions, confirms their enduring value. Astronauts view these missions as very important.
Why? What do they get out of them?
They allow for the testing of critical technologies and human factors in a high-fidelity, high-stress environment that is, frankly, far more accessible and recoverable than space.
So what specific technologies or protocols are they testing down there that are directly relevant to a mission to Mars?
Well, think about closed-loop life support systems, scrubbers that remove CO2, systems that recycle breathable air, water reclamation technologies. These are absolutely crucial for any long-duration space voyage or a base on another planet.
Okay.
They also test communication protocols, especially those involving simulated time delays to mimic communicating with Earth from Mars. And they practice operating complex robotics or remote telemetry systems under duress and physical isolation.
It's a full-spectrum stress test for the human-technology interface, but without the catastrophic cost of a launch failure.
That's one layer, for sure. But the subsea habitat also presents these unique psychological pressures that are, in some ways, more immediate and more severe than in space.
Are severe.
While space offers the highest possible stakes for failure, the subsea environment imposes the constant, unavoidable physical threat that is tied directly to physics.
Meaning the environment itself is hostile in a way that requires constant, immediate physical mitigation.
Yeah.
You can't just float in a vacuum. You're being actively crushed.
You are. You have the intense psychological pressure of being in a high-risk, confined environment where a technological failure or even a simple human mistake can rapidly escalate. The sources emphasize that decisions made by a single Aquanaut affect the safety of the entire team and the mission survivability.
So there's no room for individual heroics. It's total system dependency.
Completely. And then there is the ultimate psychological constraint, which is the sheer impossibility of a quick escape, of a bailout. That must represent an enormous, persistent mental load.
Right. It's not like in the movies where you can just hit an emergency button and shoot to the surface.
No, that's the deadliest thing you could do. It is the defining psychological difference. If astronauts encounter a major systems failure near Earth, they're often complex but feasible abort protocols or emergency returns. But for aquanauts in a saturation habitat, physics holds them hostage.
If they head too fast to the surface, they face life-threatening decompression sickness.
Exactly. So if the team runs into a psychological crisis,
Yeah.
Serious interpersonal conflict, high stress, or major equipment failure, they can't just climb into a capsule and ascend. That multi-day, sometimes multi-week, non-negotiable decompression process is their master.
That decompression timeline is just unforgiving. For a really deep saturation mission, the return decompression can take weeks.
Sometimes 15 to 20 days locked inside a pressurized chamber, slowly lowering the pressure. That unique dynamic where the physical constraints are literally life or death and dictated by these immutable gas laws makes these missions, as the source says, really telling about human dynamics.
It's an unparalleled test of resilience, planning, and teamwork.
It is.
That truly brings into focus the profound complexity of this whole Vanguard endeavor. It's about accessing the deep ocean, sure, but it's equally about creating a dedicated laboratory for the future of human habitation in any extreme isolated environment.
And this is critically just the beginning. Vanguard is explicitly designated as a pilot habitat, which brings us to the bigger picture and Deep's expansive ultimate vision.
The pilot nature suggests a scalable and long-term plan. This isn't just a one-off experiment. It's a proof of concept. It's preparing the ground for a much larger, more permanent human presence under the sea.
Absolutely. Deep is already building larger, more flexible structures. The long-term vision involves modular, expandable habitats, a kind of subsea architecture that allows for growth and adaptation, much like the way the International Space Station grew over time.
So this implies a transition from a research station to permanent colonization.
I think so. The ultimate aim, according to Colonize, is highly ambitious and deeply transformative, allowing humans to become truly aquatic, marking a permanent human presence under the sea. This isn't about merely visiting anymore. It's about relocating a segment of civilization.
It is the final realization of that astronaut analogy she used.
It is. We need a continuous human presence to shift our collective understanding. People who live in this environment, who manage the challenges of pressure and isolation for months on end, they will fundamentally reshape our perspectives on the underwater world.
And that change in perspective comes directly from the human element. Colonize believes that the people returning from this subsea experience will be the ones who open our eyes to the underwater world.
They become the emissaries of the deep.
Their narratives, their data, and just their sheer existence as aquatic humans will integrate the subsea environment into our collective consciousness.
Yeah.
It'll transform the ocean from this remote alien place into a viable frontier for habitation and research. Okay, let's synthesize the major takeaways from this deep dive into Vanguard and the future of saturation research for you, the learner. What are the key nuggets of knowledge you should really walk away with?
Well, I think the core technical insight is that profound efficiency gain enabled by saturation diving. We are moving from a system that yielded researchers 1 hour of work for 5 hours of logistical effort,
Which is just crazy.
to one yielding up to 9 hours of continuous effective work daily, all thanks to eliminating that daily decompression penalty.
And this efficiency immediately unlocks specific science breakthroughs. It enables continuous deep-water coral restoration that was, impossible to maintain at scale before.
And it allows that true immersion in the environment to observe huge planetary rhythms, to quantify the scale and function of the diel vertical migration, and to catch those fleeting, transient events that we always missed.
And critically, Vanguard solves the data integrity issue. By providing a hyperbaric laboratory, we can finally obtain uncorrupted samples on human physiology. We can track crucial long-term phenomena like epigenetic changes and the risk of a vascular necrosis.
And that data is invaluable not only for oceanic habitation, but, as we discussed, also for future deep space missions.
So we've spent the bulk of human history limited by the physical constraints of time, pressure, and decompression, which have confined us to these brief, sporadic visits to the 70% of our planet covered by ocean. Now that Vanguard and the concept of saturation living are beginning to solve these constraints, we are truly opening the door to permanent subsea living.
So as you reflect on this new era of aquanaut exploration, maybe consider this. The technology is rapidly solving the physical constraints, the lack of time, the threat of pressure. But what will the psychological and sociological reality look like when humans live not just on the ocean, but in it for extended periods? When our bodies and our minds are forced to adapt to a permanently hyperbaric and isolated world, what new forms of human culture, governance, and understanding might emerge from these continuous aquatic communities?
That is a powerful thought. The technological leap is already underway, but the human transformation, that is only just beginning. Thank you for joining us for this deep dive into Vanguard.
We hope this provides you with the quick but thorough understanding you needed of this revolutionary step in marine science and human exploration.
Until next time.